Hi there, and welcome to my Precalculus video series, where my goal is very simple, to make Precalculus make sense. Now, whether you're here to get ahead, catch up, or just finally understand what your textbook is trying to say, you are in the right place. In this lesson, we're focusing on the real number system. And by the end of this video, you will be able to 1. Define what real numbers are. 2. Identify and differentiate between the various subsets of real numbers, which are natural numbers, whole numbers, integers, rational numbers, and irrational numbers. 3. Classify given numbers into their appropriate subsets within the real number system. And 4. Understand the significance of the real number line in Precalculus. I want you to follow along with a set of guided notes I created for this lesson, which can be found in the description of this video. Thank you for being here. Now, let's get started. I want to begin with a question. What does your thermometer, your gas bill, like when you pump gas at a gas station, and your GPS have in common? The answer is that they all rely on numbers. When you check your temperature in your house or of your body, the thermometer reads a number. Your gas bill could be $20 because you gave the gas attendant $20 for gas. And your GPS can say you have 2.59 hours left, or you could have 300 miles remaining in your journey. So each of these rely on numbers, but not just any number or any type of number. They rely on real numbers. But what exactly are real numbers? Can we consider the square root of 2 to be a real number? What about pi? Can pi be considered a real number? Or maybe a number just as simple as 0.5. Can that be a real number? Well, this is what we're going to explore today in the lesson on the real number system. Now, let's imagine an infinitely long line, an infinitely long number line, I should say. So it's a line that extends infinitely left and infinitely to the right. It stretches from negative infinity to positive infinity. Now, you should be familiar with what a number line is. So I'm going to denote our origin here. And of course, you know the positive numbers are to the right and the negative numbers are to the left. Here's the idea. Every tick mark that I just drew at 1, 2, 3, every fraction, every decimal you can create between these tick marks on the number line. So let's say, for example, between 0 and 1. Well, here you get 1/2, or same thing as 0.5. A little bit past 1, you get the decimal value for the square root of 2. A little bit past 3, you're going to get the decimal approximation for pi, and so on. The idea is that every decimal, every fraction, every root belongs to a vast and essential family that is called the real numbers. In Precalculus, this number line is essentially our entire universe that all of our ideas are going to live within. So that means every measurement, every equation, every function is going to begin and end in this real number line. I do have to add a point though, that this real number line is the universe for Precalculus for the most part. There are some ideas that we're going to learn in this Precalculus video series that will take us beyond the real number line, but we'll talk about that when we get there. So now let's take a closer look and meet what this real number system is made out of. The first type of number that we have is what we call the natural numbers. These are just simply counting numbers. The natural numbers are denoted by a capital N. And the types of numbers that we call natural numbers or counting numbers are essentially how you count. 1, 2, 3, 4, and so on. These dots I'm writing are called ellipses, and they indicate that the sequence continues on forever. So 1, 2, 3, 4, and so on. This is the innermost part of our real number system. Next, we have something that are called whole numbers that are symbolized by the capital W. Now, whole numbers are the same thing as the natural numbers with the addition of 0. So our whole numbers consist of 0, 1, 2, 3, and so on. So natural numbers live within the whole numbers. Next, we have the integers. Now, integers include all the whole numbers and their opposites. So I'm going to have ellipses that start from, they go all the way to negative infinity. And I'm just going to write down these few examples. -3, -2, -1, 0, 1, 2, 3, and so on. The integers are symbolized by the capital I. Now, here is where things get a little bit trickier, and this is the family of numbers that we call the rational numbers. And I've sort of run out of space above to continue my little diagram, so I'm going to continue them down here. I have my rational numbers. Now, let's make some quick notes about rational numbers. A rational number is simply just a fraction of two integers. So let's say any integer m divided by n. So m and n can be any two integers that you choose. So you can pick any integer to go in the numerator and any integer to go in the denominator. But there's one exception, one rule. The integer that you choose in the denominator for n, it cannot be equal to 0. And the reason why is because it makes that value of the fraction undefined. You cannot divide by 0. So some examples of rational numbers include maybe 1/2. You could have -5. And the reason why -5 counts as a rational number is because you can rewrite -5 as -5 divided by 1. You can create a ratio out of those two integers. You can get 0.25. Well, we know 0.25 is just the decimal version or the decimal value of the fraction 1/4, a quarter. You could even have numbers like 3.333 going on forever. And that may not look like a rational number, but we know that it is because this is the decimal value of 10/3, which is just a fraction of the integer 10 and the integer 3. It gives you that decimal value. So here's the key trick. If a decimal ends or terminates like in 0.25, or if it repeats a pattern forever like in 3.33333 forever, it's a rational number. Now, let's talk about these repeating patterns for just a moment. When a decimal repeats, we use a bar symbol. So instead of me having to put 3.333 with the ellipses, I could write that as just 3.3 with a bar symbol on top. This bar symbol that I just drew on top is usually called just a bar, but you can also call it a vinculum, which is spelled like this. And this bar symbol or vinculum represents indefinite repetition of whatever number or numbers that are underneath the bar symbol. Let's do a quick example. If I have the number 0.333 repeating, I could write that as just 0.3 with the bar on top. So the number that just repeats is the number 3. So that's the only number that requires a bar on top of it. Here's another example, 0.121212 repeating forever. How could we simplify that using a vinculum or the bar symbol? Well, you just need to pay attention to the pattern. So I have a 1 followed by a 2. Then I have a 1 followed by a 2. And then a 1 followed by a 2. So it's the pattern. The 1 and 2 repeat itself. So I can have 0.12 with the bar on top of both of those numbers. So you're repeating the pattern of 12, 12, 12, and that pattern will continue forever. That's what this bar symbol says. So these rational numbers are symbolized by the uppercase Q, and they build this next layer of our real number system. And finally, we need to talk about what we call irrational numbers. Irrational numbers are numbers that cannot be written as a simple fraction of two integers. So how do they fit in this diagram? Well, they don't. So they get their separate space on the outside. Irrational numbers are symbolized by the capital I. And like I just said, irrational numbers cannot be written or simplified as a fraction like the way rational numbers can. Some examples of irrational numbers would be the square root of 2, pi, the square root of 7. Now, the reason why irrational numbers cannot be rewritten in terms of a fraction is because their decimal representations go on forever. Just like the way we drew the ellipses, they go on forever, or with the bar symbols. But the thing about the bar symbols is that they have repeating patterns, like the 12, 12, 12, or the 3, 3, 3. With irrational numbers, their decimal values or their decimal representations go on forever without repeating any pattern. You will never find a pattern with an irrational number. So some examples would be the square root of 2. And the decimal value of the square root of 2 is approximately 1.4142135. And it continues on. The approximate value for pi is approximately 3.14159.265, and it continues on forever. You will never find a perfect repeating pattern in their decimals, and you will never be able to express them as an exact fraction like the way you can with a rational number. So this is the real number system. The real number system includes natural numbers, whole numbers, integers, rational numbers, and irrational numbers. We call this the real number system. So each of these numbers is a real number, but you can further classify it as either being a natural, a whole, an integer, a rational number, or an irrational number. And we symbolize all of these types of numbers using a sort of boldface R, or sort of a capital R, I guess you could say. So let's test your understanding with a quick question. Which of these numbers are irrational? 3/4, 5, 0.25, or pi squared? Feel free to pause right now if you need a moment to think. But if you're ready for the answers, let's go ahead and talk about it. Your answer should be letter D. But let's talk about why. 3/4, well, that is a ratio of two integers, and those integers being 3 and 4. And so this is already written, this is already a ratio. Therefore, it is a rational number. So that cannot be our answer. 5, it's also a rational number because you can rewrite that as 5 divided by 1. 0.25, we already talked about that example. It's also a rational number that can be written as 1/4. Pi squared is our answer because we already know pi is irrational. And so if you take an irrational number and you square it, that result is also going to be irrational. So here's the big takeaway. The real number system is the comprehensive toolbox of numbers you're going to need throughout Precalculus. Essentially, every number you're going to encounter and work with in your Precalculus course or within this Precalculus video series is going to live somewhere in this infinite real number line, except for those examples that we'll talk about much later. So now that you know what real numbers are, in our next lesson, we're going to learn how to work with them. We're going to learn some properties of real numbers. If you found this video helpful, please hit the like button and subscribe to my channel so that way you don't miss out on any future lessons on math or physics. Thank you for watching, and I will see you in the next lesson.